x approached infinity, f of x approached 0, right? And for this function, as x approached infinity, g of x, I know I probably wrote f of x there, but g of x approached 3/2. And for this function here, as x approached infinity, f of x did not approach anything. We'll just say for now, plus or minus infinity, right? It just so happens that one way to tell if, and we said that, and in these two cases, there is a horizontal asymptote because there's a distinct line or a distinct value that your y values of your function are approaching, a distinct value, 0 in this case here, and 3/2 in this case, right? So we'd say the line y equals 0 is a horizontal asymptote here, and the line y equals 3/2 is a horizontal asymptote there, right? Now, one thing that we need to look at when we determine this in behavior or whether a function has a horizontal asymptote is the degree of the polynomials here, right? Notice I got 0 here when I went through that process of finding the horizontal asymptote. And this is because, all right, out at infinity, these leading coefficients here, or these leading terms here, are going to have all of the control, right? Just like when we talked about polynomial functions and behavior. At positive and negative infinity, these other terms aren't going to matter that much. It's just the polynomials leading terms, right? So this stuff here and this stuff here is not going to matter as much. And the same thing here, okay? So what we're going to do is we're going to notice some things here and related to our outcomes. When the degree of the numerator was smaller than the degree of the denominator, this denominator here increased a lot faster than that numerator. When that being said, that means our line that our functional values are going to approach is going to be the line equals 0, y equals 0. When the degree of the numerator and the denominator were the same, our function approached this line 3/2, which is the ratio of these leading coefficients, the leading coefficient of the numerator divided by the leading coefficient of the denominator, right? So whenever our degree of our polynomials that we're dividing is the same, then I just look at the ratio of the numerator and the denominator to find my horizontal asymptote to be that ratio. And here, when the degree of the numerator was larger than the degree of the denominator, I ended up having no horizontal asymptote. Okay, so let's look at a chart so we can put all that together. It says finding horizontal asymptotes without looking at a graph and without going over that stuff where we divide by the highest power of x. We can always definitely do that, but this kind of summarizes what we need to do here. Notice I have a polynomial of degree n, so my numerator has degree n and my denominator has degree m. All right, when the degree of my numerator, the top, because that's the highest exponent, is larger than the degree of the bottom of the denominator, what we call this is top heavy. Okay. When our polynomial is top heavy, there is no horizontal asymptote. Okay. When the degree of the numerator is less than the degree of the denominator, we call it bottom heavy. Okay. And our function has a horizontal asymptote, and it is the line y equals 0. Okay. In this case right here, our polynomial would be our rational function would be considered bottom heavy, right? Because this degree is higher than that one. Okay. When our degree of our polynomial on the numerator is the same as the degree of the polynomial on the denominator, okay, there's not a top or bottom heavy. We'll just say that degrees of polynomials are equal. Then that means the line y equals a sub n, which is our leading coefficient on the numerator, divided by b sub m, which is our leading coefficient in the denominator, is our horizontal asymptote. And that was the case in this case right here, right? The degree on top equal the degree on the bottom, and our ratios 3/2 was our horizontal asymptote. And so that gives us a way to find our horizontal asymptotes. So let's talk about that last case there. For instance, when we had this example right here. When our function doesn't go to a specific value, like I was trying to explain in that other graph, there are a lot of things that can happen as x approaches infinity. Our graph can continue on up over here, it can continue on down there, it can continue on down there, or it can go down there, right? There is something special that happens when the degree of the numerator is 1 more than the degree of the denominator, all right? I already know that there's no horizontal asymptote, but these graphs have a special thing that happens, all right? And it's called an oblique, or some people call this slant asymptotes, because we have horizontal, vertical lines, right? And then lines can be slanted as well. That's right. And so these occur in rational functions where there is no horizontal asymptote. I'm going to abbreviate that with HA. And the degree of the numerator is 1 degree higher than the degree of the denominator. Okay? In order to find oblique asymptotes, we got to figure out what's happening at infinity. Okay? As x approaches infinity or negative infinity. And one clever way to do that is to actually perform the division on the polynomial and see what happens. So what we're going to do is we're going to use long division, or we can use synthetic division if synthetic division applies. Remember, if you have a denominator in the form x minus c, and your c is a real number, then you can perform synthetic division. All right. The byproduct of this is the actual line that is your oblique or your slant asymptote. Slant asymptote may look like this, or it may look like this in your xy plane, is that the line y equals your quotient after you perform your division is going to be the oblique asymptote. Okay, so let's put all this stuff together and let's find all asymptotes of a rational function. And so we're going to start with this example here. It says f of x equals -2 over the polynomial x squared minus 5x plus 6. We want to find all of our asymptotes. Okay. And so what I'm going to do is I'm going to first start by finding my vertical asymptotes. I'm going to abbreviate that with VA. Remember, we have to factor our numerator and denominator. Here, our numerator is already factored. Our denominator will factor in x minus 2 times an x minus 3. Nothing cancels, and so I'll set both of these factors equal to 0. And I'll solve for x. And then those are my vertical asymptotes. Remember, these are lines, right? So the lines x equals 2 and x equals 3 are vertical asymptotes, right? These are lines, these are not points, so I'm going to write them as their full equations, x equals 2 and x equals 3. Those are our vertical asymptotes. Let's find the horizontal asymptote, okay? If there is one. Remember, we're thinking about end behavior here, and basically we have to look at the degree of the numerator and the degree of the denominator, right? So you don't necessarily have to write all of this down, but my degree of my numerator, I'm going to abbreviate that with NUM, is 0 because that's a constant function. All right, you can think of that as -2 times x to the 0 power. And my degree of my denominator is 2, right? So this function is bottom heavy, meaning as my function goes to infinity, I'm going to have -2, and as x approaches positive infinity, over a big number like that. So when we divide a small number by a really large number, it approaches 0, right? And so just like we said, when it's bottom heavy, the line y equals 0 is the horizontal asymptote. All right. We can also think about oblique asymptotes, but in this case, since there is no, since there is a horizontal asymptote, there is no oblique asymptote. Okay. So we found all 3 of these asymptotes here. Let's go to part B. I'm going to change part B up just so that we can have some things that happen here that are pretty important. I'm going to say that this is going to be x squared plus x. This is going to be x cubed plus x squared, and I'm going to change this to a +1 here. A +1, right? And so we're going to start by finding our vertical asymptotes. That means we're going to factor our numerator and denominator. Remember, we can factor by grouping, and just to speed things up here, our numerator factors into an x plus 1 times an x squared plus 1, and our denominator factors into an x plus 1 times an x minus 1, right? Now, remember, for vertical asymptotes, we have to cancel our common factors. So I'm going to cancel these two factors here because they're in common, and I'm going to end up with f of x equals x squared plus 1 over x minus 1. All right? That means this x plus 1, if I set it equal to 0, because it's not going to be in my domain, right? But it's not going to be a vertical asymptote. It's going to be a hole in our graph. Remember, we're trying to find the vertical asymptotes here, so I'm not going to worry about the hole, but that is what happens to x equals negative 1. It's a hole in the graph. It's not in our domain, so it's a possible candidate for our vertical asymptote, but in this case, it is a hole. Here, now I only have one factor in my denominator, which is x minus 1. I'm going to set that equal to 0, and I'm going to see that x equals 1. This line is my vertical asymptote. So I got a vertical asymptote, it's x equals 1. Let's go to the horizontal asymptote, okay? Remember, you look at your degree of your numerator and your denominator. In this case, we are a top-heavy function, rational function. When it's top-heavy, there is no horizontal asymptote. No horizontal asymptote. And so we just don't have one. Our graph is going to go either to positive infinity or negative infinity as x approaches positive or negative infinity. And so now what we're going to do is we're going to look at our oblique asymptote. And our oblique asymptote is only going to occur when first we have no horizontal asymptote and the degree of the numerator is 1 more than the degree of the denominator. And that is actually the case here. And so what we're going to do is we're going to use long division or synthetic division to help us determine what our oblique asymptote is. And what I'm going to do is I'm going to go back to the original function and do the long division on that, because here I can't use synthetic division. This isn't in the form x minus c. And so I'm going to come, right? Remember, we always replace our missing powers of x with 0, right? So I'm going to have a denominator here, my divisor, and my dividend is x cubed plus x squared plus x plus 1. And so I'm going to perform long division. Remember, the first question you asked is what do I get when I divide x squared into x cubed? I get x. Remember, you can always go to the side and do that math there. Then you multiply. When I multiply, I'm going to get x cubed plus 0x squared minus x. Do my subtraction. Remember, I put it in parentheses because I've got to distribute that negative to each of these terms. And I'm going to end up with an x squared plus 2x, because that's going to change to a plus. X plus x is 2x. I start the process over again. But before I do that, I can bring down my next term. And I'm going to see how many times does x squared go into x squared. That's 1. So I'm going to get x plus 1. I go back and multiply. 1 times x squared is x squared. 1 times 0x is 0x. And 1 times negative 1 is negative 1. I'm going to subtract. That cancels just like that canceled. 2x minus 0x is 2x, and 1 minus a negative 1 is plus 2. And I am finished because I have no more terms to bring down, and x squared doesn't go evenly into 2x without a remainder, okay? I'm going to stop here. And so what I get here is that this original f of x can be written as x plus 1 plus my remainder, which is 2x plus 2, over my divisor, x squared minus 1. Now, to see what actually happens as x approaches infinity, or negative infinity, notice if I look at this part right here, this part right here is now bottom heavy. Right? So this part would go to 0, and then this part right here would be left going to infinity. And so this is what my function is going to approach as x approaches infinity. It's going to approach what the line y equals x plus 1 approaches. And so this is actually going to be my oblique asymptote. It is my quotient for when I do long division or synthetic division. In this case, we did long division. And it's our quotient when we do our long division. This is the line that our function is going to approach, because the remainder over our divisor is going to approach 0. So this is going to be the control at positive and negative infinity.